discussing methods to solve nonlinear equations. So, that is solutions to nonlinear equations in one dimension. That is what we have been discussing. So, just briefly go over the methods which we discussed in the last class, and also some of the implementation of these methods in the form of programs. That is what we will be looking at today. So, as you remember that such numerical solutions are necessary because you cannot always get closed form solutions to nonlinear equations just as in the case of a quadratic equation. So, numerical methods to solve them are absolutely required, and we said that there are 4 different methods to solve or achieve this goal, and they are basically graphical methods, methods of successive bisection, Newton-Raphson method and iterative method, Newton-Raphson's iterative method and secant method. In fact, all these methods are iterative except the graphical method, in which you could simply plot a function and then look at the zeros or where do they cross the x axis. In the case of one dimensional function which we are discussing here, this is rather useful to get a rough estimate. And then we looked at method of successive bisection, and this bisection methods which we looked at basically the fixed point iterations, and then we also looked at the mean value problem. Okay, so we looked at the two methods of doing this, and that is what the implementation of that we will see in a few minutes. So, in the bisection method, actually there are two. One is bisection method, so 2 iterative methods. In that one is bisection method which we looked at, in which we just said that we choose or we make 2 guesses, that is x0 and x1 as the 0 of the function, or where the function crosses the x axis to be. And we will choose x0 and x1 such that it is on either side of the root, right. And we then take the mean of this as the new iteration point, okay, and then look at the function value at this point, and if the function value at this point is negative, then we replace x0 by this point, and the function value at this point, that is f of x2, is positive, then we will replace x1 by that point, and that is what we saw. So, because we have chosen x0 and x1 such that f of x0 is less than 0 and f of x1 is greater than 0. That is, if you actually go and look at some function of this form. So, let us say we look at a function of this form, that is 1 minus x squared minus plus log 10 of 1 plus x. Okay, so, we had a function, some function of this form, we will just plot it from 0 to 2, and then we will plot a 0 axis on that. Okay, so so now that's the x axis, right. So, that is the 0 line. So, we want to get this point where this function crosses this axis, right. So, that is what we want to get. So, we basically want to get this point where this function crosses this axis, okay. And then it turns out that the one way to do that is to use this bisection method. So, we will make a guess of where this is, this crossing point is, and that is taken as x0 and x1. So, we have to choose it such that x0 is on the side where the function is negative and x1 is on the side where the function is positive. So, we have to make our initial guesses on either side of this crossing point, and that is a drawback of this of this particular method, that we need to have an idea of where the function, the 0 of the function is, and then we have to choose it's on either our initial guesses to be on either side of this point. Okay. So let's just look at an implementation of this code first, okay, and then we will go and then look at other methods. Okay, so here is a code which would it's a midpoint or bisection method. Okay, so here is a code which does that. So what I have done here is to write the code in such a way that there are two function calls, okay, in this code. Okay, so that this midpoint is our method. So midpoint method is been put into a function. So the main program here simply takes an initial guess. It asks you to feed in two initial guesses, and you have to feed in this initial guesses x0 and x1 such that f of x0 is negative and f of x1 is positive. That is, it's on either side of the desired root. So if there are many roots in this program, this program assumes there is only one root. If there are many roots, we have to make this many calls depending upon how many roots the function has. So we need to have an idea about how many roots a function has before you make a call like this, a program like this. Okay, so this scanf function will, as you know, we have seen it before, just reads of x0 and x1, okay, from the screen, and then it feeds that into this function called midpoint, okay, which has been defined, which returns the solution. So since this midpoint function returns a solution, we need to define that we have to find what variable type it returns, and it returns a floating point, and hence I have defined here, declared this midpoint to be a float variable. Okay. And now this midpoint function, which finds a 0 using this bisection method or the midpoint method, and that function need to know what is the function for which it is to find the root, right. So that is a user defined function. So that has been passed, that is written in another function called func here, and this program needs to know what that is. So you note this here. So I have called, so I am passing this variable here. So there is func is declared here, okay, as external. Okay, this is declared external. This is again a float. This is also a variable type. Okay, we will see why it is so. So this is a function. This returns the function value at any point. Okay, so func basically has my function, whose 0 or whose solution I need to find, whose 0 I need to find. So that is supplied in another function, okay, that's called func, and then func is that a pointer to that function is passed to the midpoint. So this main program itself does not call this func, it is called by this function called midpoint. So that's the idea. Okay, so it needs to know what that function is, and that has been passed here. Okay, so now when this midpoint function takes it, it takes it as function. Okay, so you could give any name here, but it takes it as function, and then it calls that function program. Okay, so that's the idea. So let's look at the structure again. So we have two functions here. One is midpoint, that's a method. Okay, now this is going to be a general structure for one or two programs we look at. That we have a function called one function which tells you the solution to the 0 of your equation, and that could be midpoint method or fixed point iteration method, or it could be Newton-Raphson, or it could be secant method, any method which you are going to look at. Okay, for different methods there will be different functions. So this main program simply calls one of those functions here, passing the initial guesses, okay, and a pointer to a function which contains my f of x, for which I need to find the 0. So this is just a passing pointer to that thing. So we have seen this in the initial part, the programming part, that how to pass a pointer to a function to another function. Okay, that is what this is. So, I am just passing the pointer to that function here. So, now here is a midpoint function, and again I told you that this is supposed to return a floating point variable. So, I typecasted it as float, and similarly this midpoint is supposed to return the floating point variable, which is a 0. So, again I declare it as floating point. Okay. So, then this is the main thing. This is very simple. We know that all you need to do is to this function, all you need to do is to take x2 as x1 plus x0 by 2. So, that is our method, right. So, we have initial guesses x0 and x1, which is passed on to this, and this, okay, now this pointer to this function, the one which gives you the function value. Now, this program here you could give any name, it does not matter, right, and you just call. Okay, this is just a pointer which is passed on to this. Okay, so, here you could give any name. So, that is the idea. If you have a package, if you are writing a package to find the roots of the equation, then you could give it any name here. The user need not know that what your name you are given. Okay, you just have to, the user has to define a function, some subroutine called fu, whatever, in this case I called func, and pass a pointer to that. Okay, so, then this function returns a float, and it takes an argument which is float. Okay, so, that is what it is. And then what I have derived some error to my error estimate here, start with, I just initialize it to 1, and then I say that you do this loop till this error is some user defined tolerance which I given as 0.0001, 10 power minus 4. So, this error is defined as, if you remember, is the initial guess minus the new guess divided by the new guess, the absolute value of that. That is the error that we have declared here. For example, it could be x0 minus x2 by x2 or x1 minus x2 by x2, depending upon, after the first iteration we are going to replace x0 or x1 by x2. So, x0 and x1 are our initial guesses, and we come here and we compute x2 as the mean, the midpoint between x0 and x1, x0 and x1, and then I compute the function value. Now, I look in the function, I am calling this function here f of x, function of x2. The function of x2, when I call, you look at the function of x2, the function is, when I say function here, it actually calls func, because function is a pointer to func. So, it calls func with an argument float x. So, that is a value, x value at which you want to evaluate the function, and the function is evaluated at that point as 1 minus x square plus log to the base 10 of 1 plus x. So, that is our function, the function which we just now saw, that is 1 minus x square plus log to the base 10 of 1 plus x. So, it just computes the function value at that point and it returns it. That is what it is doing. Okay, so, this function, so whenever you call function from this program, from this subroutine called midpoint, and it is actually calling func, because we have passed a pointer to this function func as to this program. Okay, so, it computes that. So, we determine the new x2 value as the midpoint between x0 and x1. It computes the function value at that point, it evaluates it, and it looks at whether it is less than 0. If it is less than 0, then the x0 is replaced by x2, right, because f of x0 is negative. So, if f of x2 is negative, then x0 is replaced by x2, and so the error would be x0 minus x2 by x2. On the other hand, if function f of x2 is greater than 0, then we will replace x1 by x2, because f of x1 was positive. So, we will replace now x1 by x2, the new x1 value will be given by x2, and the error is x1 minus x2 by x2. Okay, so, at each of the iteration step, okay, I print out the error, the new x2 value and the function value at x2. And then once it satisfies this error condition, that error is now less than or equal to 0.00001, okay, it returns that x2 value and comes out of this program, and it goes here, okay, and that is our answer, and the 0, and the main program will let us print it out, the 0 of the function is function as whatever it gets as s here. So that's the idea. Okay, so let's see that how this works. So we'll just compile this and then compute it. I'll call it midpoint.c minus lm because I'm using log 10. It needs a math library. So we'll run this program now. So that is we'll say dot slash a dot out. Okay, now the program is now waiting for 2 inputs. So let's go back and see. So it is waiting for this function here at this variables x0 and x1, and remember f of x0 is negative and f of x1 is positive. Okay, so that's what we need to give. Okay, so f of x0 is negative and f of x1 is positive because we are going to replace here whenever the function value is negative, we are going to replace x0 by that. Okay, and when the function value is positive, we are going to replace x1 by that. So x0 f of x0 is negative. And if you plot this function, we have seen that in the earlier case. Okay, so it's where the 0 is around between 1 and 2, and so we'll give it as 2 and 1 as the initial guesses, because f of 2 is negative and 1 is positive. Okay, so that's what the output is. So that's the iteration step. So we have the initial iteration is we gave the initial values as 1 and 2, and so the initial iteration should be, the first step should be 1.15, that was the initial midpoint rule is, and the function value there is negative. So we'll replace f of x0 by, so x0 by 1.5. Okay, we had x0 as 2, okay, so that is going to be replaced by 1.5, and then we evaluate the function there again in the second step, and the function value is still negative. So we are going to replace now x0 by 1.25, and then the next iteration the function value is positive. So the function value is positive. So we are now going to replace x1, that is 1, by 1.125. So that's the way the iteration proceeds, and we can see that the error, which is in this case it was x2 minus x0 by x2, and in this case x2 minus x1 by x2, is decreasing monotonically. So the function value itself is also going towards 0, and then thus we will converge pretty fast and monotonically into the value 1.154724 as the 0 of the function. Okay, so that's the midpoint rule implementation. Another method which we looked at that time was method of false position iteration. After this we look at the fixed point. So this false position iteration, we had a slightly different idea to find the 0. That is, again we have guesses x0 and x1 such that f of x0 is less than 0 and f of x1 is greater than 0. So that was the same as the bisection or midpoint method we just looked at. But we don't here take the mean of x0 and x1. Okay. Instead, what we were trying to do here was to draw a line from x0 f of x0 to x1 f of x1 and find the point at which this crosses the 0 axis. Okay. And then we replace that as our new x1. So that's what we were doing. Okay. So we had we'll just look at that the method, the false position method, the summary of the method. Let's say we have an f of x like this. Okay, then we'll pick up 2 trial points which encloses the root, right? And then evaluate the function f of x0 and f of x1. Make sure that they are on either side of the 0. Okay, and then what we did was, so now it's like this. Okay, now we have a function like this, some function like this, and then we just picked up x0 and x1 values. Okay. That is just some guess. Okay. We made sure that f of x0 is positive. In this case, okay, f of x0 is positive. Is on either side of the 0. In the programs, we are taking this as x0 and this as x1, and then we draw a line from this point to this point. Okay, we just draw a line like this. We'll just draw a line, and that line, where that line crosses the, if you have a line here, and that line crosses the x-axis, that is somewhere here. Okay, so that would be the next guess. Okay, and now if this value, this is my x2 now. So my x2 will be this here, where it crosses the 0 axis, and that x2 is now replaces x1 because that is for that x2 value function is here. In this case, it's negative. Okay. So that's the method which we're going to look at now. So we'll just look at an implementation of this code here. Okay. So that is called the false position method. So we'll have the program here, false position. Okay, so in the false position method, again we have exactly the same structure. That's what I said in the thing in the earlier program. So we are just going to only thing we are going to do is replace this function which we had called there as a midpoint method. Okay, we are going to just simply replace that by a false another function called false position, and again pass to this program the pointer to our user defined function, which is again we take as 1 minus x square plus log to the base 10 or 1 plus x. So we will minimize the same program, the same function, we will find the 0 of the same function as what we did in the midpoint method, but we will use a new function called false position. Okay. So that's what we are going to do. So in this function again, what we do now that here is again it returns a floating point, so it's typecasted as float here. Okay, and so x0 and x1 it reads off because it also needs two guesses. Okay, both this midpoint and this false position needs two guesses. So we'll give that as x0 and x1 on either side. We'll again choose f of x0 to be negative and f of x1 to be positive, like in the other case. Now this function here, so gets this new x value as now. So this is by solving the equation of the line connecting these 2 points, which we just now saw, the equation of the line connecting these 2 points, okay, with the x axis. So we know how to write equation of a line connecting 2 points, and find where the crossing point of that with y equal to 0 line, which is the x axis. So that gives us this particular formula. Okay, so that gives us this formula for the new value x2 as x1 plus f of x0 into x0 minus x1 by this is actually f of x1 into x0 minus x1 by f of x1 minus f of x0. Okay, so this is our formula. Okay, and in this case I had taken f of x1 as positive and f of x0 as negative. Okay, so that's the formula which you put in here. Okay, and then that function value, then again if the function value is negative, then we will replace x0 by that, and the error is x0 minus x2 by x2. We just saw this in the midpoint. None of this has been changed. If the function value is positive, I will replace x1 by x2 and then find the error as x1 minus x2 by x2, etc. And we will print out here again the error, the new x2 value and the function value at x2. So I have not changed the function. The function is the same, 1 minus x square plus log to the base 10 of 1 plus x. Okay, so the idea is that we can use the same, we just have to replace this program here and just pass the pointer to that function, user defined function. Now if I want to minimize some other function, I don't have to change anything in this program. The only thing I have to change is define a new function. Instead of this func, I would define a new function, and then pass the pointer to that function to this program. Okay. So we'll see how we could what we get from this. Okay. So we'll now compile that false position. So we compile this program here, and now we will just run this program. And again, as in the earlier case, it's just waiting for this two initial guesses x0 and x1, x0 on the negative side and x1 on the positive side of the function. So again, I will give the same initial guesses 2 and 1, okay, and then run this, and you can see that the method, the false position, converges pretty fast. So when we ran the midpoint method, it had to go through many iterations, but here the convergence is much faster. Okay. Even though both have linear convergence, which we will see soon, this particular method converges much faster, and we of course get the same answer. So again, this is monotonic. The convergence is the error decreases monotonically. The function value goes to 0 monotonically, and we have the 0 as 1.154694. So that's the second method which we saw. We saw this thing, and then Okay, we look at some other method. So that is the fixed point iteration. Okay, so we look at that. So that's something which we again saw in the earlier lecture. So this fixed point iteration. So we'll just go through that. We'll summarize that what we saw in the last lecture once again before we look at the program. So in this method, we want to write the function f of x equal to 0, which we have to solve, or we have to find the zeros of this function f of x. We want to replace that by a function, an equation of this form, that is x equal to gx. Basically, what it's saying is that I should be able to write f of x as x minus gx, and I will say x equal to gx. So this I will use to get my iterative step. That is, you start with one guess. Now I don't need two guesses. As we saw, one problem with having a midpoint or a false position method was that you need to have two initial guesses on either side of the 0. So that's more difficult to do. So we will now be looking at methods which needs only one guess, okay, and it can be on either side of the 0. Okay, so that this is for this fixed point iteration is one such method, and where we just make one initial guess and use this form. It's kind of a mapping, okay, and then we'll use this form to generate the new value. Okay, so if x, the guess is actually the 0 of the function f of x, then x should be equal to g of x. Right, because now we replace function f of x by g of x minus x. So if x is actual 0 of the function f of x, then x should be equal to g of x, and the iteration would stop. Okay, we will again look at the error as the same one as before, that x old minus x new divided by, or xi minus xi plus 1 divided by xi plus 1 mod as our criterion for error. Okay, so error is defined as that, and that has to go less than some value which we define. Okay, so that's the thing which we will again, so that's the method we will implement here, and then we will look at that code again. So similar structure, we will look at this fixed point iteration. So that is this program. Okay, again I have not changed anything except changing this function name now to fixed point. Okay, so I just replace. Each time I want to replace it by a different method, I replace this particular program, this particular function, which is my fixed point, which is now is fixed point iteration. And there's some slight changes. It's like, we now need only one initial guess, so we don't need two initial guesses, and we have to pass only that. And this function, this fixed point, this function will then return the solution to me, which I print out here. Okay, so again we have to pass the pointer to the function which you want to look at, or we want to find the 0 of. Okay, that is func, same as before, that is 1 minus x square plus log to the base 10x. But now we need to write that as x minus g of x. So what this function should now return is g of x. Okay, so there are some changes. So let's just go through this once again. We have the main program which calls this method fixed point, and it passes one initial guess and a pointer to a function which returns now g of x, not f of x. Okay, so that's the now then it goes to the fixed point, that function. Okay, now this function we initialize the error to be 1, and we demand the error to be the same as 10 power less than 10 power minus 4 for this as a criteria to be satisfied. Okay, so now we use x equal to g of x here. So x2 equal to f function x1. X1 is our initial guess. So that is, this function is now actually g of x. Okay, so that means I need to write my 1 minus x square plus log 10 of x in the form of x minus g of x, okay, and then write g of x. That's what I have done here. So now I have written it as 1 plus log 10 of 1 of x, 1 plus x divided by x. Okay, that's my g of x. You can see that this minus x is my f of x, right? So this minus x equal to 0 is my old f of x equal to 0 equation. That is this function here, 1 plus log to the base 10 or 1 plus x by x minus x equal to 0 is the same as f of x equal to 0. So, my g of x is 1 plus log 10 log to the base 10 1 plus x whole divided by x. This is the x divides this starting from here to here. Okay, so that's a function. Okay, so now we will use this mapping, that is x2 is function x1, and now we just have to replace always the new function. Now we don't check whether the function is negative or positive before we replace the old value, because there is only one guess here. Okay, so the error is simply x1 minus x2 by x2. Right? So that's all we have to do. I will print out the error, the new x2 value, and the function value at x2. And then remember that now we call x2 as x1, and I computed the error, and then I had to replace x1 by x2 now, because the next round when I had to go, right, I had to call the new x1. So I had an initial guess. That initial guess is now replaced by x2 here. Okay. So this is the next guess that is returned by the function. So that's a fixed point iteration. In short, it is just writing xi plus 1 is equal to g of xi, checking whether this is actual 0 or not. If it is not, and I replace xi this value by this value and continue the iteration. Okay, let's run this code again. So like before, we will run this code. So now this is fixed. Okay, so now we need to get just one guess. So let's just give it as 1. Okay, so it goes through that and gives us the 0. Okay, so we need to give only one guess. I could also give the guess as 2 or anything. Okay, so it gives me still the same 0. So I'm just doing this iteration. Right. So now remember, this will not work all the time. It worked in this particular case, but we know that it may not work all the time. And as you can see, it is not much faster than the. It is not much faster than the. At least for this function, it is not much faster than the false position method which we looked at. It had to go through many iterations before it reaches there. But the advantage, of course, is that we need only one guess, and that's a big advantage when it comes to functions for whose graphical form which we're not able to see, or the function itself is returned by some other program. Okay, so we don't know where the 0 is, so we cannot bracket it. Okay, in that particular case, this is definitely a great advantage. Just to have just having to guess 1 point instead of 2 points. But remember that it has a drawback, and the drawback being that if in the cases where it is the slope is greater than 1. Okay, so if it's for a function like this which has 2 zeros, let's say, so this particular case it will converge to that. But when it is somewhere here, when you have to find out this point, okay, it will not converge very easily. So remember that what we are doing by this fixed point iteration is actually finding the intersection of two lines, that is y equal to g of x, okay, and y equal to x, right? That is equal to x equal to g of x. If you find the x at the intersection point of these two lines, that is y equal to x and y equal to g of x, we basically have an equation that x equal to g of x, and that's what we want to solve for, right? Okay, and we find that when you have intersection points like this, where the slope of this g is greater than 1, we saw this in the last lecture, that this will not converge, okay, and it will diverge. So this is not guaranteed to give you a solution all the time. Okay, so that's the method. That's the methods which we looked at last time. Okay, and then we briefly saw some other methods. Okay, so we will now go into another method which also again uses only one initial guess, and that is the Newton-Raphson's iterative scheme. So in the Newton-Raphson iterative scheme, we again make only one guess. Okay, so let's say that's x0 we took it as. Okay. So what we're going to do here is to actually draw a tangent at this point. Okay, that's the basic idea of Newton-Raphson point. You make one guess and draw a tangent at that point to this line. Okay, so that means we need to find the tangent to this line, that is the derivative of the function at that point. Okay, and you extend the tangent all the way onto the x axis and find the point at which the tangent meets the x axis. Okay, so that, and then take that as your next guess, that x value as the next guess, that is the function will be somewhere here then, right, and then you draw another tangent, okay, and find where it meets the x axis, and then you find the function value there and draw another tangent, etc., till you reach the 0. Okay, so that's the basic essence of the Newton-Raphson method. Okay, so that's again summarized here. So we will determine some. We will first make an initial guess, determine the slope or the tangent of the function at that point x equal to x0. Let's call that as f prime of x. And then we will get the next root there, okay, by using this formula. That is, we will actually finding the point at which that tangent meets the x axis. Okay. So that's what this equation results from. Okay. So x1 equal to x0 minus f of x0 by f prime of x. Okay. Basically, what we are trying to do is we are expanding the function f of x using a Taylor series and keeping it only up to order 1, okay, and then saying that my f of x plus delta x is f of x plus f prime of x, the derivative of x at x into delta x, okay, and saying that f of x plus delta x is now 0, or we are assuming that, okay, or we are solving or finding the intersection of this line, of this tangent line with the x axis, and that will result in a formula x1 equal to x0 minus f by f prime of x. Okay, so that's the general form. So in general, we would write it as xi plus 1. In the iteration scheme, we will write it as xi plus 1 is given by the previous guess xi minus the function value at xi divided by the derivative of that function at xi. Okay, and that of course, as before, the iterative cycle is stopped when xi plus 1 and xi are almost same, or f of xi vanishes. Right? F of xi goes to 0, then xi plus 1 is equal to xi, and that's where the iteration would stop. Okay, so now we could see the implementation of this. Okay, so in a code. Okay, so as I said that the essence of this is that we will say that f of xi plus 1 is actually f of xi plus h. H is the delta x, the change in x, which is I expand in a Taylor series, right, and then I terminate it here, and I say that goes to 0. So my error in this particular case would be of this order, and then I solve for this. That's what I am doing. Okay. So there are cases again in which this function this will not work. Okay. And we will see that particular case implemented and then the use of that. Okay. So before we look at the disadvantages of Newton-Raphson method, we will just see one case where it is implemented. Okay, so that is, let's show the program here. So that is called Newton. Okay, so here is the function. Okay, so again I use the same structure. I have the main program which will take in one guess. Now again we need one guess here, just like in the fixed point iteration. Okay, and I call this function here. I pass this. I call this function Newton here and pass that my initial guess and a pointer to my function. Okay, that is to be whose 0 I need to find. So now what does this program do? This Newton, this part which uses the Newton-Raphson method to find the 0 of the function. Okay, so now it calls the function. Okay, so now this function which is to whose pointer we have passed on to this function as. Okay, now here. Okay, now that has been called here. So now we call that function. Now this unlike the earlier case where the function was returning just the value of the function. Now we also need the derivative. Okay. Now for the time being, you forget these two lines. I will come to this later. We are using now a function of the form x minus exponential minus 2 star x. We are trying to find the solution of this equation. Okay, that is x minus exponential minus 2 star x equal to 0. So, that is what you are trying to find, or our function is to the zeros of which we want to find is x minus exponential minus 2 star x. Okay. We will not use 1 minus x square plus log 1 plus x at this point. We will just find the solution. We will find the 0 of a different function here. And now I need the derivative of that function. So, the derivative is given as 1 plus 2. So, the derivative of this, so that is 1 plus 2 exponential minus 2 star x. Okay, so, now this function call is slightly different. So, let me explain this. So, this function, this the new FUNC which we have in this particular case, okay, is not returning anything. Okay, so, it is void. Okay, it does not return anything. So, it is unlike the previous case, we have declared it as float because it was returning a floating point number which is a function value. So, this particular function is not returning anything. It takes 3 arguments, okay, 1 floating point and 2 pointers, 2 floating points. Okay. That is what it takes as argument. Okay. So, that is what has been declared here also. This is a function, this is a function, this function calls that name as function, and that has 3 arguments, that is float, float star and float star. Okay. So, that 3 arguments x1 is what I pass into that function, okay, and f the function value at x1, and the derivative of the function at x1 it returns through this thing. Okay. That is, it replaces f by the function value at x1 and it replaces by the derivative of the function f at x1. That is what this thing is doing. So, you can see that here. These are pointers. So, these are all, see this y and derivative are pointers here. So, that is y star y, right, the asterisk y equal to x minus exponential minus 2x. So, it gets this x value and it gives this, computes this y and derivative at this point, okay, and replaces this here. Okay, then it goes back. So, when it goes back to this function, now when it makes a call here, it comes with the new f value at x1 and derivative value at x1. So, I uses that to find the new x2 next x value, x1 minus the function value by its derivative. Okay, note the asterisk f because these are pointers. Okay. So, now I have the error as absolute value of x1 minus x2 by x2, and I am just printing that out, and I replaces x1 by x2 just like the fixed point iteration scheme. So, the difference between the fixed point iteration scheme and this is only in this step here, that is here the new x2 value is x1 minus star f plus star f divided, that is asterisk f because it is a pointer, f by derivative of f, that is what in short it is. And then I computed the derivative, the new error, okay, and then I print that out, and the iteration scheme continues till the error is less than 0.0001. Right. So, we'll run this code and then we'll see. Okay, so again it needs a guess. Okay, so we'll give guess as 1. Okay, and that is, so now this is a different function. So okay, I think we should just plot this function and to see. Okay, so our function was, if you remember, so the one which you are trying to solve was x minus exponential of minus 2x. Okay, so we'll plot that function. Between 0 and 2, let us say we plot it. Okay, so the function is like that. Okay, so we will draw the 0 axis. So, that is a function which you have. We expect the solution to be somewhere less than 0.5. Okay, that is the x axis. So, somewhere here is the solution which is less than 0.5. Okay, that is what we are trying to find. Okay, so we ran that and we got the solution to be 0.042, 0.42. And notice that, so I am printing out more than one variable here. Okay, so I am printing out here the error, the new x1, x2 value, the old x1 value. So that's the old guess, this is a new guess, the function value and the derivatives. Okay, so that's what been printed out here. So the function value goes to 0 and the error goes to a value which is less than the tolerance which we had defined. in just 4 steps. So, this is definitely much faster. Okay. This is a really fast way of computing the zeros, okay, and the most often used method than anything else, okay, because it needs only one guess. Okay, it needs only one guess to be given of the 0, and that guess can be anywhere, and it converges very fast when it converges. Okay, so, that is the advantage of this, is it converges very fast and it needs only one guess. Okay, so, now there are some disadvantages, and that is what we want to look at here, that it can get into an endless cycle, okay, or it can even diverge in cases. So, that is, we will look at some pathological cases like this in this program. Okay. So, here is a case where it can actually get into an endless loop. Okay. So, let us say we want to find this, our initial guess happened to be here, okay. We want to go here, okay. We want to find a 0 which is here, right, and we do not know the functional form. So, we just made an initial guess which is here. So, what is the method? The method is to draw a tangent, and that is what this blue line is showing you. I will draw a tangent, and the tangent you can look at, it meets the x axis here, right. Okay, when I draw a tangent at this point here, and it meets the x axis here, and then I take the x value to be that, okay, then I draw a tangent here, and that meets the x axis here. So, but then it goes back here and it meets the x axis here. So, it keeps iterating between these 2 points. Right. So, we can get into an endless loop in this particular case. See, another case can happen in which, for example, we look at this another function. So, we look at our old function which we called as, which we had 1 minus x square log of 1 plus x. Okay, so, let us look at that function. Okay, so, we look at this. Okay, so, now in this particular case, okay, now if I make an initial guess, let us say here, okay, and then also I can get into trouble, because if I make an initial guess, okay, so now that's a very large value, somewhere very down there. Okay, so the tangent here meets the x axis somewhere very much down. Okay, and then, so that's one case. So, we can actually diverge. Okay, so if you for example make a guess somewhere close to this, okay, then the value at which you are going to get where the tangent is going to meet the x axis, and that is going to be extremely large number. Okay, and then we can get into an error. Okay, so there's 2 cases. So, you will see actually in this case, if I make 1 minus x square plus log x, if I try to run this, and it does not converge. So, there are 2 pathological cases which I can tell you, that if you have initial guesses are somewhere close to where the second derivative vanishes, okay, and then you can have very small f prime and get into an error, because remember our function, our method requires f by f minus f prime to be found, right. So, that can give us a large error. So, that is one reason why you can get this when you go here. Okay, so, we will see that just a minute. So, that's formula which you are using. So, if f prime is very small, okay, then also we can get a large error in this, and we can diverge, we can go to a very large value, and then things can diverge. That is one case where it can get into trouble, and another case which we saw that it can get into a infinite do loop. Okay, so, that is another case. So, in this case, for example, if you take this particular function 1 minus x square into log x, and we will actually have trouble using Newton-Raphson method, but other methods would work. Okay. So, another way to is, and then another disadvantage of this program of having using Newton-Raphson is that we need to compute f prime of x, that is the derivative of x. Okay. So, when the derivative of x is not available, okay, we will again have problem with this method, because this function value might be returned by some other program, and we do not know what the derivative is. Okay. So, in that case, we may have to make an approximation to derivative by what is called a difference method, okay, a difference approximation to a derivative. Okay. We will see more of this later when we look at differentiation and integration. So, here for the time being, let us take this formula which is known to most of us, that the derivative we replace by what is called a backward difference formula. Okay. That is, we take the f of xi minus f of xi minus 1 divided by f of xi minus f of xi minus 1. So, now this formula is a backward difference method if a difference formula if xi minus 1 is some value which is less than xi, okay, and then we would call this as a backward difference formula. But in this particular case, in this iterative scheme, xi and xi minus 1 are simply just two guesses, two guesses in the ith and I minus 1th iterative steps. But this is a formula which we can use. So, the f of xi is the one value xi, and xi minus 1 is another value. So, we make two guesses here to start with. We will guess xi and xi minus 1, and then we will find this function, this derivative f of f prime as f of xi minus f of xi minus 1 divided by xi minus xi minus 1, and we will use the Newton-Raphson formula again as xi plus 1 as xi minus f by f prime. Okay. So, the idea is that we will not find f prime exactly like in a function, okay, but we will simply replace that f prime by this particular formula f of xi minus f of xi minus 1 divided by xi minus xi minus 1, okay, where to start with xi and xi minus 1 are our guesses. Okay. Now, what is the difference between this and the false position method? That the false position method we made two guesses and we did something exactly like this. This is again going to be the line connecting xi f of xi and xi plus 1 f of xi plus 1, line connecting these these points xi f of xi plus minus 1 f of xi minus 1, and this line, where does it meet the x axis, and that is the point going to be our new iteration point. Okay. So, that is, in the false position we made two guesses, that is x0 and x1, and we said f of x0 at the line connecting x0 f of x0 and x1 f of x1, where it meets the x axis is our new x value. Right. And this is exactly the same in that sense, that we are again going to use two guess values, okay, x0 and x1 let us say, and we are going to draw a line connecting these two, okay, and we are going to take the point at which that meets the x axis as our new guess. Okay. So, but what is the difference between then this new method which we call the secant method and that the false position method is that these two guesses x0 and x1 does not have to be on either side of the 0, it can be anywhere. Okay. And hence, it also has a disadvantage that it might not converge. So, it can just get onto the same side of the 0 and it may not converge, and that is what the disadvantage of this is. Again, we will go through the details here. Okay. So, it is similar to the bracketing method, but we do not bracket here. So, the advantage that we do not have to know where the 0 is. So, we do not have to worry about whether we are actually bracketing it. On the other hand, it has a disadvantage that it may not converge, while the bracketing methods are guaranteed to converge. So, here is the formula which you are going to use in this particular case, and that is being graphically shown here. Okay. So, you make some guesses xi minus 1 and xi. Okay. So, it does not have to be on either side of the 0. Okay. In this particular case it is, but it does not have to be on either side of 0. So, we draw this line here, okay, where it meets the x axis. Okay. And now, one more difference from the false position method is that this xi plus 1 now will replace xi and xi. So, now xi minus 1 now is go to xi and xi plus 1 will go to xi. So, xi will go to xi minus 1, xi plus 1 will go to xi. Okay. So, we will always replace the last one. Okay. So, that is in the case of false position, the new point, if it is on the means on the negative side, that is below the x axis, then we always replace x0 with that. Okay. But here there is nothing like this. So, the first these 2 points were taken, right, and then these 2 points will be taken, okay, and then we found a new intersection point, right, and then we will take now these 2 points, etc. So, we will continue like that. Okay. So, now we will draw a line like this and we will go here. okay, and then we will draw a line like this and we will go like this, etc. Okay, in this case it will converge, but in the false position method, remember that we always replaced, if the new iterative point, that is the point at which this meets the x axis, if this is less than 0, that is the function value is less than 0, it replaced x 0. If it is more than 0, then it replaced x 1. Okay. But here we do not do that, we always replace the last point with the new one. Okay. So, irrespective of whether it is less than 0 or greater than 0, we are going to say that the next line we are going to draw is between xi and xi plus 1, and the next line would be between xi plus 1 and xi plus 2, etc. Okay, that is a method, okay, and we will see an implementation of this and cases, the pathological cases, both this and the Newton-Raphson method where it does not work in the next lecture. Okay, we will also do a more analysis of what is the convergence rate of these three of these methods which we have looked at so far, okay, between the bracketing methods and the Newton-Raphson and the secant methods. We will see that in the next lecture.